So we're going to look at how we can use integration with the motion, so the kinematics. In the Moodle site, um, my co-teacher has put up some conjecture questions. They're very good. They are very important to do. Can you give me a tick? Have you noticed those conjecture questions put up and some other past exam questions for integral calculus? Anyone notice that in the Moodle site? All right, so please go and look for it. Um, So I've also put up a practice test, and when I wrote the practice test, I knew about the questions that were in the Moodle site. So the test doesn't necessarily cover those same things. So please have that in mind that you need to do those practice integral calculus past exam questions plus the practice, which is longer than 60 minutes, but it will give you a good revision. But when I talk about revision, I do advise you revise the lot, and when you believe you're ready, do the practice test. And I recommend that you do it against the time, and then when the time's up, you go back and find out, do the rest like an assignment. I haven't put the solutions up yet. Um, yes, I'm not sure when. It probably won't happen till the weekend for the solutions. Any questions about like how this term is going and ending? Okay, so I would like you to look at this graph and what can you say is happening? So use the facts that are presented on the graph to describe what is going on. Would you do that in text chat? Have a go at writing something about first thoughts are fine. Any thoughts are acceptable. So you can just do the very beginning. You don't have to do the whole lot. So first thoughts about what is happening on this graph. I'll do that. Thank you, Pete. And welcome, Brett. Thanks for getting us started, Hannah. But Hannah, would you please write your comment to all participants so that we can get ideas off of each other? So first thoughts are excellent. And quite often our first thoughts, they lead to the next one. And when you say something in general terms, then you can get more specific. That's good, referring to the formula. So now that you've noticed that it's velocity versus time, and he slowed. So Brett, thank you. How did he slow? So now let's get a bit more detail. So we've got an idea. People haven't started using numbers yet. So um, can you talk about the quantities? What initially and finally? All right. So try and add and put more detail into those comments. Good. So initially he was traveling at 60 kilometers per hour. That's good. Yes, this detail's good. 6 minutes to come to a stop and a linear rate. So it was a regular constant rate of slowing. Now, we're integrating. So, what is the meaning of the area under that graph? If we integrated a velocity time graph, what does it take us back to? Yes, so it takes us back to distance. So when you integrate velocity, you go back to distance because I don't know if this helps, but remember that if we have a function, and I'll use the physics notation, a displacement function in terms of time, and we find the derivative of that, the derivative of displacement is velocity. So now if we integrate a velocity time graph with respect to time, we will go back to the displacement function. Oh, can I have a tick? Do you follow that integrating it, the area underneath is going to be the displacement function? All right, the next thing to notice is if we integrate this linear function that Pete noticed, then when we integrate the velocity function, we will get 60t minus, well, it's going to go to t squared, and we're going to divide by 2, 300t squared, plus the constant of integration. So the displacement function, it's got a negative in front of the t squared. Can people, I know there's not a lot of space, but can you do a sketch on the whiteboard of the shape of this displacement function? A really rough sketch. Don't worry about scale or anything, just the shape. That's all I want you to be aware of. So we've got a linear function drawn. Let's see what else people think. Remember that the displacement function is in the form 60t minus 300t squared plus c. Now, you might be used to having the t squared written first, minus 300t squared plus 60t, where t is the variable time. Do I have any other shots at the shape of that function? Yes. Now, there's one more thing to add. So that's part of a parabola, and people are lowering it. It's negative, so that's it. It's going to face downwards. Now, we don't know what C is, so we don't know whether it's up, whether the vertex is up or down, because C could be a negative number. So we'd need a bit of extra information. Now, why I wanted you to do that is when we're doing conjectures, you've got to take time to read the graphical information. And you've got to let it sink in. You've got to notice the important things. So it's when you get your test, you might see that the number of marks aren't 1 mark per minute, because conjecture and applying your knowledge, there's some thinking time. And so be aware that there is time, a bit of time allowed for you to interpret the problem. Okay, so do you want to have a go at illustrating the information here can you read and highlight this information? And then again, I want your first thoughts. What do you have to notice to start to draw a graph for this? So I'll give you a bit of time. Starts from rest. Yes, leave that up there. So actually rides off from rest. So accelerating at a constant rate. So all right, thank you. There's a little bit much there. That's good. All right, so that's possibly, I think people are still reading through. Now, the person who's begun to do a scale, can you tell me your first thoughts? Who's starting to do that scale? So, Brett, what were your thoughts to help you decide your scale?
So you've got your maximum point of 40 k's per hour. So that gives us our y-axis max. And we've got somewhere there it says, oops, for 5 minutes, unless I skim read it too much. So 5 is our scale for our x-axis.
All right, pause there, please, Brett. Thank you for those thoughts. Does anyone want to add to Brett's thoughts? So Peter's saying total time. Do people want to look back and reread the information? Because that's what happens. You have a first thought and then you say, hang on a minute, that's not quite right. I need to add to it. So let's look at the time. A constant rate for 3 minutes and got up to a maximum of 40 kilometres per hour, which is a velocity. Then she maintains a constant speed for 4, so we're up to 7. All right. That's it, Peter. 15 minutes. All right, so we're working out the scale, and that's what you do. You get a holistic view, and then you zero in on the bits of information you need. So we can adjust the horizontal scale. Now, the other thing that Brett talked about was X and Y, but can someone say what should be plotted on the X and Y axis?
This is too early in the morning, Jan, for testing my brain. So the independent variable should go on the x-axis and the dependent variable should go on the y.
Excellent. So let's add to Brett. What is the independent variable? What is the thing that we're sort of measuring that we're deliberately noticing change? And what changes as a consequence? Displacement from Hannah, or is that old? Oh, that's old, sorry.
Measuring displacement.
Yeah.
Or we can determine displacement, but we're measuring time.
Yes, measuring time.
Sorry, time. Yeah.
Yeah, so it's time that is going to go on the x-axis. And I think Hannah's comment, sorry, was an old one, so that was a distractor from me.
Knock it off, Hannah, you're distracting.
I wasn't. Oh, sorry. Okay. Well, actually, we're talking velocity all the time. Do you agree, Hannah, that we're actually talking velocity versus time, and that's what we're going to be plotting? Oh, thank you. Yes, so she did. I'm glad that you read each other's text chats. Now, and then hasn't been said yet, but you've got to get the units right, and the time is in minutes. So, all right, you need to be aware. All right, now I hope that I've got on the next slide a picture that matches. No, I haven't, drats. So my main point is you've got to break it down, you've got to think carefully, you've got to make a start, and then once you've made a start, I actually hope that the next little bit Let's try and do it quickly. It starts from rest. All right. And constant rate for 3 minutes until she reaches 40 kilometres per hour. So 3 minutes. Oh, we haven't got our scale right. That's got to go up to 15. So, Brett, why are you saying that? Because is it not showing? All right. I can't see a graph. Let me just refresh my screen. My apologies. I see no graph. So, do others see the graph? All right. Hit enter and it might show. All right. So, yes, I only see a rectangle. So, I'm going to continue. So, after.
Hold on, it's coming.
Okay, thank you. Hasn't come yet. Ah, yellow line. Excellent. Up to 40 and the scale of 3 minutes. Here, that's good. So I don't know if your scale is going to appear. 5, 10, 15. And now we get to what Hannah was saying. If we integrate that, we're going to find the area under the function, and the area under the function is going to be displacement. Thank you very much for doing that graph. So now if we're going to look at displacement, and so we've got a velocity function and we're going to integrate it, so the area under the velocity function will give us what? So what do we need to consider to find displacement? Let's do that first. If I asked you to find the displacement from 0 to 4, so I'm making, instead of a general statement, I'm now making it a particular statement, a definite integral, because people can often think initially in the definite and then generalize later. But when we go to conjecture, that's the process you'll do. You'll look at a definite situation and then you'll try and say how that is true in general. So here we go. We're going to integrate the function t squared minus 3t plus 2 with respect to time. So if I ask you for displacement, what does that mean in terms of that definite integral? All right, take the integral. Yes, Hannah, well done. And will the integral, if you just put it in your calculator, will the integral find displacement or will it find distance? Do you understand the difference? Any comments? Actually, Pete, it won't. If you find the integral from 0 to 4, it will find this positive area here. It'll find this area here, the integral will be negative because it's below the x-axis, and then up to 4, it'll find this positive area here. So the integral from 0 to 4 will have that area, take that area, plus this area. So if I call this A, area B, area C, area A is positive for the integral, area B will be a negative area C will be a positive area. That will give you displacement. Can I have a smiley face? Do you follow that that will be displacement? So displacement has direction. If we wanted the distance, we'd need the modulus. And there on your calculator, there is an absolute value. So let me show you how to use that. I'm not sure if I do it on the next slide, so maybe not. So can you get out your graphics calculators? Here it is. And you might like to write down that integral. I'm going to need to. T squared minus 3t plus 2 from 0 to 4. All right, so let me get rid of the rubbish on my screen. So if you go on the emulator to the run menu, make sure that the run menu is in math mode, and I'm pretty sure the emulator is, mine wasn't, so it's in math mode. I want to do a calculation. So the option button, I want to calculate using a definite integral, t squared, so I'm going to use x instead of my t, minus 3t plus 2, and I want the absolute value. Now, I might have done things in the wrong order. I have, sorry. I need to do the absolute and then enter the function into it. So let me just delete what I've written there. So now I want actually to exit. I'm still in the option button. I want number. I want it to be an absolute value. So F1 chooses absolute, and I get the two straight up lines for absolute. Now I can put the function inside of the absolute symbol, and absolute just makes it all positive. T squared minus 3t plus 2, and I want to go from 0 to 4. Now this should give me distance because I've taken the absolute value. I get a distance of 5 and 2/3 if I want it exact. So you've got to need to recognise that 0.6 recurring is 2/3, and that is distance. Now if I do displacement, I expect a smaller number. So if I go back, oops, and I put my function in, and this time it should be displacement. And I get 5 and 1/3, which is just a tiny bit less, and that's the displacement. Do you feel confident to use the absolute function on your calculator? Because I guess this is recorded. I will send it so people might want to look back. But the option button in the run menu has all those sorts of number calculations behind it. But it's the concept that I want you to understand. So if for some reason you had to do this problem by hand rather than using your calculator and you are asked for displacement, then you do the integral just of the whole thing. If you are asked for distance, then you will do the integral from 0 to 1 of the function. I'll say let the function be f of h just for interest. So I'll just write f of h. Actually, I should write f of t because it's in the variable is t. All right. Then I would have to take the integral from 1 to 2 so that I get a positive area. Take the integral from 1 to 2 of my function and plus the integral for the last little bit of between 2 and 4. And always write with respect to t on the end, which I didn't do here. All right, can I have ticks? Do you follow that when you've got to understand whether the area is positive or negative? So, or the integral of the area is positive or negative. I'm going to ask these displacement questions. We've done the derivative, we've gone forward. It's exactly the same process going backwards. And I want you to understand doing it by hand, but doing it on the calculator is so much quicker. So in your weekly work, make sure you do a couple of questions the long way by hand so that you really understand what is going on, but then use your calculator. All right, so I have actually on these slides given the instructions. Okay, so most of today's lesson is understanding what you're reading because you can't do applications problems unless you understand where to start. So could you again quietly read this question and highlight the key bits of information? Yeah, I'm reading Brett's text chat. It is really good to do that linear motion diagram and think it through. All right, a fair number of highlights there. So part A, what do you do to find the speed of each animal after 1 second? Yes, and both Hannah and Pete have replied, and Pete has emphasised that you put it into the velocity function, and I like that aspect. When you're doing these problems, you need to say, what is what is the question talking about? And part A is talking about the function that is there. It's talking about the speed function because we haven't worried about direction. So the speed is given as v of t. You put in the 1 second instead of t. All right. So part B. Show that the lion's speed decreases over time, whereas the zebra's speed increases over time. How are you going to work that out? Yes, you could find acceleration. Thank you. So it's derivative. That's right, Hannah. Excellent. So we're doing an integral calculus topic, but we still have to know when we can use the derivative. So that is definitely one method. The derivative of velocity gives acceleration, and if it's negative, then it's slowing down. Excellent. There's more than one method. Can anyone suggest another method? Yes, sign diagram for the velocity. Excellent. You could also do a sketch of the function to show that the function is decreasing and slowing down. So more than one method. I think Hannah's method is probably the quickest. Both Hannah and Pete's methods are quite quick. So part C, find the integral from 0 to 3 of the speed function, the first speed function, which is the zebra one. Who can interpret what that is going to find? And if you actually, let's do that. Let's, on your calculator, let's find the integral of 0 to 3 of the first speed function for, sorry, the lion. The lion is v1. Yes, sorry. Yes, that's right. In the first, Hannah and Pete, you're doing a great job. Has anyone calculated it? I haven't calculated it yet. Partly because I'm a bit like Hannah. I don't know where my calculator is. I think I've left it home. I have to use the emulator. All right, there are good comments there. So has anyone finished that calculation? So put it in text chat and I'll do mine. I'm only just starting now. Oh, a whole heap of us with no calculators. Well, I'm just using the emulator, which is a bit slow. 15e to the minus 0.1t. So that's the other thing I want you to notice, that all of the functions that have been using, including trig and natural log and exponential, your integration applications can use all of those functions. And when you're using the exponential function, just be careful. Have any of you got stuck with it staying as the power? Just notice that after you've put in your exponential value, that you've got to press the across arrow so that the power stops. There it is. I'm using an old formula and actually it's not as quick as I thought it would be. Okay. 0 to 3, 15e to the 0.1x. I left out the negative. all in agreement there, 38.9. And the units for the speed is meters per second. And if you put in the units, it helps you to keep track of what you're talking about. Thanks. That's good, Hannah. All right. So you've interpreted it. And people have gone on and you've talked about one going faster than the other and bad luck for the zebra. Okay. Oh, well, I don't know. I'm assuming. So part G says, does it catch the zebra? So you can follow the logic through. Okay. Now this question is looking at a roof gutter, and it talks about the cross section of the roof gutter is defined by. So it's saying that the function that defines the shape is this function down here. So the language of this question is just, you've got to interpret it a bit carefully. It's not actually talking about the area of cross section, it's talking about the function that defines the area. And from -5 to 5 centimetres. So I'd like you to practice using your calculator and see, actually the first thing I'd like you to do on the whiteboard or on your own piece of paper might be quicker, can you write down the function to calculate the cross-sectional area? So I'll give you a little head start and then I'll write it and just check that you've written it in the right manner. So have a look. Can you give me a tick if you've written down the area function? On the older calculators, yes, I like to put the brackets in just to show that you're doing it of the whole lot. Okay, so smiley face. Did you realise that the area was compared to the x-axis and it was below, so you take negative of it? Now there's two ways to do that. There's a couple of ways to do it. I've taken the top function is y equals 0, so I've said 0, take the bottom function, and the bottom function is the fx. So can I have a smiley face? Did you put the negatives in? Okay, I'm assuming the no response means you haven't done it yet. So just remember that when you're working out the area, you're working out the area between two functions. And the top function on this occasion is the straight line y equals 0, and the bottom function is f of x. So you are doing an integration from -5 centimetres to 5 centimetres of the top function, which is 0, minus the bottom function with respect to x. So can I have a tick? It depends if you're a little bit behind on your weekly work. Do you understand that when you're working out the area, it's the top function, take the bottom function? Yeah. Okay, so that's something that some of you are just consolidating now. All right, so off you go, please. Can you, on your calculator, find that area? Okay, I'm hoping to see some text chats of the area that you get. Yes, 100 divided by 3 is exact. Well done. And then the last little bit, and I want you to notice this, the last little bit is really quite straightforward. What do you do to answer part B? That's it. Multiply by 20 gives you the volume and it'll be in units cubed. So let's say for some reason you got really stuck, you couldn't find the cross-sectional area, part B is probably worth 1 mark. You can just say, let the area be A, then the volume is A times 20, and it's in centimetres. So actually, I copied Hannah, and I didn't need to, because if I look at the units, it's centimetres all along. So really, it's going to be centimetres squared. All right, and then when we do the volume, it's going to be 20 times the area, and the units will be cubed. Now I need to stop here. Oh, actually, I've done it. So just a repeat of what I said at the beginning of the lesson, that nearly all of this week's work is not new, it's applying your understanding. And it is absolutely essential because going backwards, when you're integrating going backwards, things like if you have a function g of x, and then I must stop, and you say if f dash of x, let me think, is g of x, then these points here, when you integrate and go back to f of x, those points on g of x, those zeros, if you're going back, does anyone know what the zeros will be on the f of x function if you're going backwards with integration? I'll tell you they'll become actually the opposite way. We're going backwards. They might be an inflection. They will be stationary points because it's 0. So they're a point of change. So it'll be a local maximum, a local minimum, or it could be a stationary inflection. All right, so we don't know whether it's a maximum or minimum without other extra information, but that ability, and that's what you're going to do in the weekly work. You're going to practice some of that going backwards and interpreting the graph and what it means when you go the other way. And we'll do a bit more of that next week in lesson, and we'll make sure that solutions go up into the Moodle to the questions that are there. No worries. All right, I have another lesson. I better not be late for that one as well. Okay, people, have a really good week. Keep the questions coming during the week. Do you want to say goodbye to each other?
See you, everyone.
See you guys.
Bye, everyone.